7a, the logistic one. This is the one where, I can't even remember what it is, but we got liters of something over months. And so, they gave us an equation and they told us the units. They gave us one particular point. The thing that got me was they said the word logistic. So I immediately started thinking, if I have a differential equation that's logistic, this is what the actual function would look like. And this is one way that you can solve it. But take a look. Other than the fact that they have f and t and we have y and t, you can sit there and say, those aren't quite the same. This says 6 minus f, and I have a 1 here. So if I'm really going to write this equation the correct way, I will probably have to factor out a 6 from inside the parentheses. I'll have to rewrite it so that it says this. And if that's the way that I rewrite df over dt, then writing this equation over here will be super easy. I know L is 6, and by the way, that's the carrying capacity. I also know that 2 is equal to k. And my equation's almost done. I could actually find b by just plugging in 0 for the t value and 3 for the y value. But I'm going to stop here for a moment and look at what part A is requiring us to do. We need to find a limit. So I rewrote this so it didn't say y. I don't want to be too confused here. That is f, if we use the correct variables. So if I want to find the limit of this, as e approaches negative infinity, e to the negative infinity, on an exponential graph, that gets really close to 0. It doesn't even matter what b is. When t approaches infinity, this is going to be 6 over 1 plus something close to 0. So the limit is 6. And now when we want to find the limit of this, as long as f is approaching 6, we can plug 6 in here and say, oh, well, that's going to be 2 times 6 minus, the function of 6 divided by 6. That's 0. But there's an easier way. Imagine this. If you just imagine the logistic graph, if you do just enough here to find out the carrying capacity, we know that as the function goes on forever, it gets closer and closer to that carrying capacity of 6. So if you know this, you don't even have to solve for the equation. Just know the carrying capacity is 6. We also know that the slope here flattens out to be almost horizontal. So the derivative, the slope there of that function, as you go farther and farther out, approaches 0. Now, when is it increasing most rapidly? You can look for the inflection point. When does it go from concave up to concave down? Or you can say, hey, it's right here. So if you look on there, all you need to do is determine, how do I find df dt? Well, let's plug in f is equal to 3. That's the height of that function. The function is 3 at that moment. But hey, again, when you plug f equals 3 into your function and you get 3, make sure you put down the units, liters per month. Then we come to the second derivative. And, if this is our first derivative, you can do this one of 2 ways. You can look at this and say, I'm going to use the product rule, because these are multiplied together. Or you could rewrite that, multiply it out like this. Take your pick. No product rule here. Now you got a square. Oh, no big deal. But this is just a fancy way of saying, hey, take the derivative. So I'm going to try this one. The derivative of 2f is just 2 times whatever function this is. We're using the chain rule. That's 2 times the derivative of f minus 2/3 f times the derivative of f. Well, that's crazy, because what should I put in for the derivative of f? Well, what I had up here. If you stop there, you have the answer. That is the second derivative. Remember, folks, you don't need to algebraically simplify on the AP exam, but you would need to substitute in what f prime would be.